Hello everyone, and welcome to a lecture about navigation from space. My name is Gregor Möller, and today I would like to give you an insight into global navigation satellite systems, such as GPS, and I will explain why these systems are so useful for navigation. Over the last 30 years, the number of GNSS devices has continuously grown, from the first Navi in 1989 to about 6.4 billion GNSS devices in 2019. Based on current predictions, this number will further increase to about 9.5 billion GNSS devices in the next 10 years. This means, on average, each capital will have at least one GNSS device. So we can immediately see that the satellite navigation is still a growing market, which is of interest not only from an economical point of view, but also enables a series of applications. To understand why GNSS is so attractive, we have to look more carefully into the specifications. First, global navigation satellite systems allow us to compute our 3D position and velocity, but also accurate time information on the microsecond to nanosecond level. In addition, GNSS is available everywhere on Earth and even above the Earth, as long as GNSS signal reception can be guaranteed. Furthermore, GNSS has been designed in such a way that it works under all weather conditions and allows for an unlimited number of users. Well, I assume that most of you are familiar with the use of GNSS, but maybe do not know so much about the technical realization. Thus, in the following I would go more into detail how this performance can be achieved, and I will demonstrate that with the right equipment and processing, not only meter but centimeter position accuracy is possible. From the basic concept, GNSS is a time measurement system. When we know the travel time of the GNSS signal from the satellite to the receiver, we can multiply it with the speed of light and obtain the distance of the user to the satellite. This sounds trivial, but from one measurement alone, we cannot compute the 3D position, but only the sphere around the satellite on which the user must be located. This is illustrated on the left side for one satellite. In consequence, multiple satellites have to be observed at the same time, and only the combination of 3 measurements gives us the chance to determine the user position. Conditions therefore is that the satellite and receiver clocks are synchronized, but usually this is not the case. In consequence, the measured signal travel time is slightly incorrect. This is the reason why we call the measured distance in GNSS positioning pseudo-distance or pseudo-range. To compute the correct distance, an additional observation to a 4th satellite is necessary. This allows us to compute and to correct for the receiver clock error and to obtain our position. The general method is known as position fixing based on pseudo-ranges. I'm sure most of you have already heard about GPS and maybe also about the other 3 global navigation satellite systems, namely GLONASS, Galileo and Beidou. In fact, all 4 systems are based on the same measurement principle. To guarantee global coverage, each system is realized by a constellation of 22 up to 44 satellites as of August 2021. The satellites are well distributed over several orbital planes at a distance of about 20,000 kilometers. To give you an impression how a nominal GPS constellation looks like, let's have a look on the following animation. In this animation on the left side, we see how the GPS satellites are distributed over 6 orbital planes. In addition, for a user in North America, the number of visible satellites is shown. Due to the movement of the satellites around the Earth, with a velocity of about 14,000 kilometers per hour, and the movement of the user, the number of visible satellites changes continuously. Now, if we do this visibility study for any point on Earth, we obtain a visibility map as shown here on the right side, exemplary for one epoch in August 2021. This map shows the number of visible satellites which can be observed in the best case at this particular epoch. It varies between 6 and 16 satellites, dependent on where you are. In a challenging environment, like in the mountains or in urban canyons, the situation can be completely different. In these situations, the number of visible satellites can be significantly lower. In case you navigate only with one system, such as GPS, you might end up in situations in which a position determination is not possible anymore. Switching to multi-GNSS receivers increases the number of visible satellites and therefore reduces the risk for GNSS outages. Another benefit of GNSS is its capability to operate under all weather conditions. This might sound trivial, but requires careful selection of the signal bands. For GNSS, the so-called L-band is utilized. It is defined in the frequency range between 1 and 2 GHz. In this spectrum, the specific attenuation is low. It means the signal strength is not much affected by atmospheric water or other constituents. Furthermore, L-band seems to be very efficient in terms of performance and antenna size, especially for small form factors. In the following, I would like to show you how the individual frequencies within the L-band are distributed over the 4 global satellite navigation systems. The main message here is that each system operates on its specific frequency bands, with a few overlaps between the individual systems. As GNSS user, you have to be aware that the current GNSS receivers on the market usually do not support all frequencies, especially in the lower price range. In consequence, you have to be clear about your intended performance. In case 5 to 10 meters accuracy is sufficient for your application, a single frequency GNSS receiver might be the best choice, for example using the L1 or L5 frequency band. For higher accuracy, you should select a receiver which allows signal tracking on 2 frequencies. There are various combinations possible, for example Galileo E1 and E5A, E5B or E6. In the best case, your receiver supports all 4 global satellite systems. In addition, you should be aware that not all satellites transmit all frequency bands. The same is also true for the services provided. For example, for the new Galileo High Accuracy service, your GNSS receiver must be capable of tracking on E6. So dependent on your application, you have to decide on the right combination of frequency bands, which shall be supported by your GNSS device. In the last part of the lecture, we will have a closer look into the main error sources in GNSS. First, let's check the position accuracy possible with a single frequency GNSS receiver, as commonly used in smartphones. For recording of the GNSS data, I used an app called SensorLog. What we see here in this plot are the differences of the GNSS positions with respect to the reference position in latitude and longitude. From the scatter of the differences, the 2D position accuracy can be computed. In my test, I received a position accuracy of about 3 meters in 50% of the cases and 10 meters in 95% of the cases, which reflects more or less the expectations on such a device. To further increase the accuracy, now let's see what we can do. The position accuracy is the consequence of all error sources affecting the GNSS service. The main error sources can be divided into satellite-dependent effects, relativistic effects, and so-called propagation effects, including atmospheric delay and multipass. For centimeter position accuracy, all these errors have to be compensated, which is not a trivial task. For example, the atmosphere alone causes a signal delay of about 3 meters up to 100 meters. Since the atmosphere above 80 km altitude is dispersive, meaning the delay is frequency dependent, we can use dual frequency observations to compensate for almost 100% of the higher atmospheric effect, also known as ionospheric effect. For the remaining signal delay in the lower atmosphere, we can either use atmospheric models or estimate the atmospheric delay together with the user position. However, this requires usually longer initialization time until the solution converges. How such a precise solution looks like is shown here in this example. With the proper equipment and processing strategy, centimeter precision accuracy can be easily obtained with GNSS. However, further significant research is necessary to make this level of accuracy available to mass market applications. Since the beginning of satellite navigation, technological advancements are applied on the user side, but also to the satellites themselves. In fact, the entire constellation is continuously renewed. All satellites are replaced by new ones, with new technology, new signals, and new services for both civilian and military users. In the next few years, we can expect that smartphones will be equipped by default with dual-frequency multi-GNSS receivers. The first mobile phones of this kind are available since 2019. They allow for positioning with meter or even sub-meter level accuracy. In addition, the Galileo users will benefit from a new service called Galileo High Accuracy Service for 2 decimeter level accuracy. The necessary corrections for this service will be broadcasted on the E6 signal. The initial service will start most likely in 2022, allowing free of charge high accuracy positioning globally for everyone. In parallel, artificial intelligence and machine learning algorithms are used to further improve the GNSS data processing to provide even greater performances, not only for terrestrial navigation, but also for drone or even spacecraft navigation. In fact, GNSS works also very well for satellites in low Earth orbit. So, we expect that in the next near future, GNSS will remain the primary choice for most navigation applications, with almost 100% availability and high redundancy guaranteed by multiple independent GNSS constellations. Dependent on your demands, you will find various GNSS devices on the market, ranging from low-grade, like in your smartphone, to medium-grade receivers for centimeter precision accuracy, or even high-grade receivers for high-precision applications. So dependent on your needs, you just have to select the right equipment.